So we're going to talk more about how the rate of reaction is related to the concentration of your substances. The rate of reaction is usually, but not always, directly related to the concentration of your reactants. So the higher the concentration of your starting materials, the faster the reaction takes place. For instance, if you happen to have some hydrogen peroxide around, which pure hydrogen peroxide is actually like 40 moles per liter, not the stuff you have in your house. If you had that lying around, it would be really dangerous. It actually, with just a trace impurity or kind of a speck of dust, it can decompose explosively at a rate too fast to even measure. On the other hand, the hydrogen peroxide that you have in your house, and there's probably some in your bathroom, is about 1 molar, okay, 1 mole per liter. That concentration is significantly smaller. And at that rate, hydrogen peroxide does decompose. It makes water and oxygen gas, but it happens so slowly that your bottle of hydrogen peroxide is usually good for several months. If you leave it sitting under your counter and you open it up, you might hear a little hiss of gas, and that's some oxygen escaping, but not dangerous like pure hydrogen peroxide would be. The explanation is fairly easy to explain, I think. Reactions occur as a result of collisions. Okay, things have to collide in order to react. So the particles need to collide in order for a reaction to occur. The higher the concentration of molecules, the greater the number of collisions. So the more particles I have in a given amount of space, the more likely they are to collide, and so the reaction occurs faster. As the reactants get used up, though, their concentrations drop, and collisions occur less frequently, and the reaction rate decreases. So reaction rates get slower over time as reactants are used up and there's fewer collisions. If you remember this graph from the first video, if we look at the NO2, you can see that it's getting produced, but in the beginning it seems like the rate is really fast and then it's slowing down. Okay? If we look at just the reactant here, okay, the N2O5, again, looks like it's getting used up pretty fast and then not as fast. Okay, reaction rates slow over time. The reactants gets used up. Okay, there's fewer collisions taking place, and the reactions get slower and slower over time. So if we look at this reaction again, N2O5 plus 2NO2 gives you 1/2 O2. If you were to collect experimental data, you would see that if the concentration of the N2O5 were doubled, the rate would be doubled. We would see that it would go twice as fast. Okay? If we took the concentration of N2O5 and we tripled it, the rate would be tripled. Okay? Want to take a shot? What happens if I quadruple the concentration of N2O5? You're a genius. The rate is times 4. Well, this is clearly directly proportional. Okay? When one gets bigger, the other one gets bigger at the same rate. Okay? And we can say that rate equals some constant K times the concentration of N2O5. Okay, and this shows that when N2O5 increases, the rate increases. These two things are directly proportional. What we just wrote right here is called a rate law or rate expression. Okay, and you're going to write lots and lots of rate laws and rate expressions. Okay, rate law or rate expression. I usually call it a rate law, but you'll see rate expression quite a bit. Okay, K is a constant. Okay, and it's a different constant for every reaction at every temperature. So it's a constant that's not very constant. Okay, you would have to get it from experimental data. So if we looked at this graph that we have right here, and we've graphed rate versus concentration, you see that we get a nice straight line. Okay, what do you think the slope of that line would be equal to? If we look at our equation up here, our rate law, this would be y equals mx plus b. Okay, so your y-intercept is 0. Okay, your y is that, your x is that, so your slope of this reaction would give you the value for K, and that's how you would find K. All right. Unfortunately, for some reactions, we see a different thing happening. When the concentration of a reactant is doubled, the rate actually quadruples or becomes 8 times larger. Sometimes, when we change the concentration, it has no effect on the rate whatsoever. So how do we account for all of these different possibilities? All right. So if we look sort of generically at a very simple reaction, A goes to products. We say the rate law for this reaction, okay, is rate equals K times the concentration of A raised to some power called M. Okay? If A and rate are directly proportional, okay, so if this increases and this increases at the same rate, then M equals 1, and we say that it is a first order reaction. Okay, when I say first order, I'm merely telling you the value of M. Okay, but what if my concentration of A, when I doubled this, my rate was times 4? Okay, what's the value for M now? So 2 to what power equals 4? Well, in this case, M equals 2, and we say that it's second order. So for some reactions, when I double the concentration of the reactant, the rate doubles, but other times when I double the concentration of reactant, the rate quadruples. Okay? Sometimes when I double the concentration of the the concentration of A, nothing happens to the rate. Okay? So what would M have to be? 2 to the M equals 1. What's M? Well, M is 0. This is called zero order, and this was for the reactions where changing the concentration of A actually makes no sense whatsoever. Not makes no sense, makes no difference. Okay? So M is called the order of the reaction. All right? And it would be awesome if there were an easy way to find the order of the reaction. There kind of is, but it's not that easy. What's really, really tempting is that students like to look at the stoichiometry in the reaction, and they think that they can get the order from that. You will try it, and you will discover it doesn't work unless it's a coincidence. So how in the heck do we actually find this order? We're going to look at experimental data, and we're going to do that in the next video where I show you some examples.